Just a second. He'll just start recording and then I can introduce you and then you can begin.
Okay.
Okay, so hi everyone. Welcome to this week's talk as part of the theory seminar series. We are glad to have with us Aditi Laddha. She is currently a PhD student at Georgia Tech, advised by Santosh Vampara. And she's going to be talking about determinant maximization via Matroid intersection algorithms. So with that, you can start your talk.
Hi. So first of all, thank you for the invite. So today I'm going to be talking about our recent work on determinant maximization via matroid intersection algorithms. This is joint work with Adam Brown, Madhusudan Pedu, Mohit Singh, and Prasad Titali. Okay, so broadly, I'm going to talk about like three major things in that talk. First, I'm going to talk about the problem and how it's a powerful modeling tool. And second, I'm going to discuss some matroid intersection algorithms. And third, I'm going to talk about how matroid intersection naturally leads to a local search type of algorithm for this problem. Okay, so broadly speaking, in this problem, we're given a set of n vectors in d dimension, and the objective is to pick a subset S of these vectors that satisfied some matroid constraint M and maximizes the determinant of this matrix, which is sum of vi transpose over the selected vectors. So if you're not familiar with matroids, that's okay. In this talk, I'm going to restrict discussion about two specific matroids. Also, another assumption that I'm going to assume throughout the talk is that the rank of this matroid k is less than the dimension d. We're going to talk about mainly two kinds of matroids: cardinality constraints, which means that the subset of vectors that we are allowed to select has to be of size at most k, and partition matroid constraints. With the partition matroid, there's an associated partition of the ground set P1 to Pk, and you're supposed to select at most one vector from each partition. So as an example of this partition constraint, here, if we have 6 elements in the ground set and the dimension is 3, then here the partition is like 1, 2, 3, 4, 5, 6, and you want to select at most one vector from each of this partition. And the color of the nodes here represents what vector they are. So blue is E1 in the standard basis, orange is E2 in the standard basis, and green is E3 in the standard basis. So a valid solution with non-zero value for this instance would be when we pick a ball of different color from each part. So there are only 2 valid solutions for this instance. Okay, so another notation that I'm going to use throughout the talk is I'm going to use the symbol V subscript S to denote the D times S matrix formed by all the vectors in the set S. And when the rank of the matroid K is less than D, then the determinant as an objective doesn't really make sense because it will always be 0. So in that case, we consider the objective the determinant K subscript K, which is just the product of the top K eigenvalues of this matrix. And in general, this problem is hard to approximate within a factor of some constant to the power of dimension. And so I'm going to now go over some this problem might sound very abstract right now, but I'm going to go over some of its applications to see how this problem can be used to model a wide variety of optimization problems. So first application, probably the most natural application of this problem is in convex geometry, where you're given a set of n vectors in d dimension, and you want to pick a subset of d vectors to maximize the volume of the parallelepiped formed by these vectors. So the volume of the parallelepiped formed by like any subset of d vectors is exactly the square root of the determinant of this VS transpose matrix, which can also be written in this as sum over all the individual vectors in the set. So this problem has been studied for many years, starting with Kachian in 95, where he gave a d to the d greedy approximation algorithm. So he was studying this problem in context of rounding convex polytopes. And then a better approximation algorithm was given by D'Souza et al. In 2014, where they gave a log d to the d approximation, where they also used the greedy algorithm with pre-processing rounding step. And in 2016, Nikolov gave a e to the d approximation algorithm for this problem, where he used convex programming plus stable polynomials. Okay, so next application is determinantal point processes. So these are they're becoming more and more used in machine learning. So a determinantal point process, you're given a kernel matrix K, which is a positive definite matrix in n dimensions. And a determinantal point process associated with this matrix is just a random variable y, which takes value on the subset on subsets of n, and such that its density satisfies this equation, which is the probability that any subset of the ground set is a subset of the random variable y is so it's not equal to, sorry, it's equal under some normalization. This should be proportional to the determinant of the principal submatrix of K indexed by this subset A. And these processes are, the reason why they're so widely used and studied is because they satisfy this property of negative correlation, which is that the probability that some element I belongs to Y and the times the probability that some element J belongs to Y is always greater than the probability that both of them belong to Y simultaneously. And after some linear algebra, you can show that finding the mode of this distribution is equivalent to determinant maximization problem. Another application, which is a classical statistics application, is experimental design. So in this problem, we are given an unknown parameter theta that we want to estimate, and we can take linear measurements of this vector theta star from a fixed set of vectors v1 to vn. And when you give for a vector vi, you get an output yi, which is equal to vi transpose theta star plus eta I, where eta is there's some Gaussian noise with variance sigma square. So and from these yi's and vi's, we want to estimate theta star. So often there is a cost associated with taking a linear measurement. So for example, maybe we only have the capacity to take K measurements. So this naturally defines a matroid constraint on like the subset of these vectors on which you can take linear measurements. And so the goal of this problem is to choose a subset of these vectors under whatever constraints that we have. so that the maximum likelihood estimator calculated using that subset is as accurate or as close to theta star as possible. So it's well known that theta star is a theta star lies in a ellipsoid around theta hat, and the covariance matrix of this ellipsoid is proportional to the inverse of the summation of vi transpose. So if we want to increase the probability of being close to theta star, we'd like to minimize the volume of this confidence ellipsoid, which is exactly equal to maximizing the determinant of summation of vi star over the selected vectors. And in optimal design, this problem is called the optimal design. Okay, and the final application that I'm going to discuss is mass social welfare. So in this problem, we're given n indivisible items and d agents, and every agent I has a utility uij associated with item j, and these utilities are additive. And the goal is to find an allocation of these items to agents that maximizes welfare. And one of the most commonly studied notion of welfare is mass social welfare, which is just the geometric mean of the utilities of the agents. So this notion of welfare, it interpolates between like total utility and the minimum utility of the agent. And this problem can be modeled as a determinant maximization problem with partition constraints that was proved by Nari et al. And using the fact that you can model this problem as a determinant maximization problem, they gave a factor E approximation for this problem. However, there are better approximation algorithms for mass social welfare, which don't use this relation to determinant maximization. And the current best approximation factor is e to the 1 by e 1.45 by Berman et al. Okay, so any questions till this point? Okay, I'll move on then. So since this problem has such a wide variety of applications, there are also a wide variety of techniques that are used to solve this problem. So this is just a brief overview of the history and techniques that are present for solving this problem. So there are mainly two types of algorithms. One is convex programming-based algorithms that often use geometry of stable polynomials, and another is combinatorial methods. So also the algorithms for this problem, they seem to differ when the rank of the matroid is less than dimension versus when it's greater than dimension. So in this talk, I'm going to talk about our recent result, which uses matroid intersection-based algorithms and gives a d to the d approximation. And so this is valid only for when the rank of the matroid is less than the dimension d. Okay. So our main result is that there is a deterministic polynomial-time algorithm which given a set of n vectors in d dimensions and a matroid with rank k less than d returns a set S such that the objective over the set S is at least k to the minus ck times the objective, the optimal objective. And we used a combination of combinatorial plus algebraic techniques to prove this result. And eventually the algorithm that I'm going to present can be interpreted as a local search algorithm. Okay, so I'm going to now talk about why matroid intersection is a natural tool to consider for this problem. Okay, so from this point on, I'm going to assume that the matroid of constraints is a partition matroid, and the rank of the matroid is equal to the dimension exactly. Okay, so first of all, the problem of finding whether the objective is non-zero for the given problem instance is equivalent to finding a common basis in these two matroids. The first matroid is the constraint matroid, so which is just the partition matroid here. As I said, pick at most one vector from each part of the partition. And the second matroid is the linear independence matroid. So what this is saying is just that the determinant is non-zero if and only if there exists a set of linearly independent vectors which form a basis of the partition matroid. And we can easily find such a basis if it exists using Edmond's algorithm for finding common basis of two matroids in polynomial time. Okay, so I'm going to briefly describe Edmond's algorithm. So this the algorithm I'm going to describe is slightly different than what is usually taught as the weighted matroid intersection algorithm, but this will be easy to generalize. Okay, so here we're given two matroids, M1 and M2. So again, think of M1 as the partition matroid and M2 as the linear independence matroid. And there are some additive weights W on each element of the matroid, and the W of a subset S is equal to the sum of weights of every element in S. And assume that we've found some common basis S. This might be suboptimal, but this is just a set of linearly independent vectors in the partition matroid. Okay, so we're going to form a exchange graph for the basis S, and the exchange graph is a directed bipartite graph where the bipartitions are the set S, and the other bipartition is all the elements minus S. And now we add an edge from an element U not in S to an element V in S. So these are the red edges. If S minus V plus U is linearly independent, and we add an edge from a vertex V in S to a vertex U not in S, if S minus U plus V is in the partition matroid. So here this means exactly that the blue edges will go from any VI here to the partition, to all the elements in the partition PI, because of the property of partition matroid, this would always be in the partition matroid. And additionally, in this graph, exchange graph, we add vertex weights. So for every vertex in S, V in S, we add a vertex weight of WV. And for every vertex not in S, we add a vertex weight of minus WU. So then it's easy to notice that for any cycle C in this exchange graph, the weight of the current set S minus the weight of the set obtained by exchanging on that cycle, S minus delta C, is exactly equal to this the weights L that we defined here, sum of all the weights L on every vertex in this graph. So what this means is that if the set S is not optimal, then there has to exist a set then there has to exist a cycle C such that the weight of S delta C is greater than the weight of the set S, right? So if S is not optimal, then there exists a negative weight cycle in GS, and if there exists a negative weight cycle in GS, then S is not optimal. So by here negative weight cycle, I mean that the sum of the weights on all the vertex on that cycle is negative, which is the right-hand side of this equation in blue. Okay, so using this, I can describe Edmond's algorithm now. So we initialize S with any common basis, and here S is all the vertices in orange. And if there's no negative cycle in this exchange graph of S, then you return S as the optimal solution. But if there exists a negative cycle in GS, then here I'm calling the blue edges are form a negative cycle. So you select C to be the shortest hop negative cycle, and then update S to S delta C. So now this is the new set S delta C in orange. And we keep on iteratively doing this step till there are no negative cycles in the exchange graph of S, and then return S. So the fact that
Aditi, quick question.
Sorry, yeah.
Yeah. So when you say short, like I know this for the shortest paths in exchange graphs, and this is so that's why I'm asking. Like the standard presentation probably looks at these shortest paths. What do you mean, like specifically? What do you mean when you say shortest hop negative cycle? So among all negatives.
Yeah, I mean, among all the negative cycles in this graph, this is the cycle with the minimum number of edges.
Okay, it's not the other. It's not like the so it certainly can be the case that there is a even shorter cycle with which is positive weight. So it's you're looking at all negative weight cycles and then among them picking the one which has the shortest number of edges. Is that?
Yes, exactly.
Okay, and it's the same, like it's the, like in the Matroid union algorithm and such, it's the shortest path, so it's the same. Like analogously here, it works for this sort of shortest hop negative cycle. Like you can't exchange any like cycle, right? Like this is sort of crucially required for the like the S delta C to be like a common basis. So
yeah, that was my next point, that like till now I haven't really used any property of the Matroid in describing this algorithm. So yeah, exactly like you said, when C is like the minimum hop negative cycle, which is a negative cycle with the minimum number of edges, that implies that C delta C belongs to the intersection of both the matroids. And this is like the crucial property for the success of this algorithm. But yeah, thank you for the question.
Yeah, and so just to be like pedantic here, you can you just quick, I'm sure it'll take me a minute to figure out, but nonetheless, like how do you find this efficiently? Like so negative cycles we can, negative length cycle, like if I impose this additional constraint.
So you can use like Bellman port. So like the Bellman port has this very nice property that you're like increasing the number of edges in the walk, right? So it's like the first negative cycle that you find in Bellman port is the cycle that you're looking for.
Got it. Got it. Okay. Yeah. Makes sense. Thank you.
Thank you. Okay. So so this property that C is a minimum hop negative cycle implies that S delta C belongs to the intersection of both the matroids. So I just want to say that while this is important, this is not the main. I guess I am not going to touch upon this point again because I'm just going to talk about partition matroids, because before we even get into this point, working with determinants presents challenges just because determinant is not a sub-additive function. So I'm just going to talk about the techniques that go into, but I still want to use this algorithm to approximate determinant. So I'm just going to talk about the techniques that go into adapting this algorithm for determinant. Okay, so now for when the objective is determinant, so now weight of any subset S is log of determinant of Vs transpose here. I'm going to use exactly the same exchange graph as defined before. So the graph that I described before, the structure of the graph did not depend on like what the weight function was. Only the weight that you put on vertices depended on what exactly the weight function was, right? So again, I'm just going to describe this graph one more time. So in this graph, we have our current basis S and the set of all the elements minus S on the left-hand side. And there is an edge, a forward edge from any element in U minus S to any element in S if S minus V plus U is linearly independent. And there is a backward edge, a blue edge from an element Vi in S to all elements in Pi minus Vi, where Pi is the partition that contains Vi. Okay, so first thing that you might notice is there is no concept of a vertex weight now, right? Because you cannot separate determinant over these rank 1 matrices that you get from every vertex. So now I guess an important observation here would be that we can reinterpret the algorithm with additive weights as you were weighing an edge from vertex U to V to be exactly the change in objective when you just exchanged U and V, like when you just exchanged these two elements, whatever the change in objective was, that was the weight of the edge. So in the same vein, we're going to use the same weight for the edge. So the weight of an edge from a vertex U in the right-hand side of the graph, sorry, in the left-hand side of the graph to a vertex V in the right-hand side of the graph is going to be the change in objective when you replace vertex V by vertex U in the current solution. And now, because our current solution S is linearly independent, we can uniquely decompose any vector U as a linear combination of the vectors V in the current solution. So these AUV, which is the coefficient of V in the linear decomposition of U, these coefficients would be unique. And so this is a purely linear algebra based lemma, or you can also see this geometrically. But for any U naught in S and a vector V in the current basis S, the weight of the edge from U to V should be minus log of the absolute value of this coefficient. And by should be, I mean this is exactly this change in objective that I was talking about in the last slide. Okay, so these weights are still not additive in the sense that the change in objective, when you change on more than one edge, it's not equal to like the sum of the weights of those edges, right? And just for the ease of notation, I'm going to define cycle weights as just the product of the coefficients on the edges. So basically, I've removed this minus log here from cycle weights. And so now, when we are going to talk about cycles, I just mean the product of the coefficients of all the forward edges on that cycle. Okay.
Aditi, quick question again. So
Yeah.
these are not additive, but they are also like the inequality can go both ways, as in the difference of the log determinants can be more than this, and as in some cases, and can be less than the sum in other cases. Is that true? Or I'm wondering
Yeah.
how far.
Sorry, what? Why do I take what?
No. Okay. So I'm saying that can I replace this not equal to by like less than equal to always, or that is not possible?
No. That's not possible. But like you said before, it's quite possible that in some cases it's greater than equal to, and in some cases it's less than equal to. But
Okay. Okay.
yes. So okay, yeah. I'll just say the punchline is that we if we find the cycle cleverly, then we can replace this not equal to by approximately equal to. So like 1 plus minus small o of 1, and yeah. Okay. So that's what I'm going to talk about in the rest of
it's
it.
not it's not submodular either. So it's like I'm just wondering if there's some log concavity for this that gives me like some sort of submodularity, and even that is because the following problem, I believe, I mean, check me on this, but I believe has been looked at. Like you want to find like maximize a submodular. So instead of additive weights, you have a submodular function, and you want to find a common basis. So these things, I think, have been looked at.
Yeah, there is a constant approximation for the problem you're talking about. If it's a,
right.
But yeah, the problem here again is that this is not a submodular function. This is a sort of a funny function that like it is submodular in some regimes, like when the size of the set is less than d, then it's submodular. When the size of the set is greater than d, it's like submodular. By submodular, I mean it satisfies like this principle of diminishing margins, but like at D, it does not satisfy diminishing margins. So like overall, you cannot say this is submodular. So yeah, this is kind of a funny function, but yeah, that's a good point. Okay. So okay, so again, to re-emphasize what we're trying to do here is that we took Edmond's algorithm for additive weights, and now we're trying to see it from the perspective of determinants. And so now this, the second bullet point here, if there is no negative cycle in the exchange graph of S, then you return S. This is simply not true, because you cannot, like we just discussed before, we don't know that inequality is true in either direction. So rather than working with negative cycles, we take a slight relaxation and we say, okay, we're fine with short cycles. So I'm going to concretely define short cycles in a moment. But the core lemma in for additive weights was S is not optimal if and only if there exists a negative cycle in this exchange graph of S. But for determinant, we'll give a similar lemma, which would be S is not close to optimal if and only if there is no short cycle in GS. And by close to optimal, I mean whatever the final approximation factor we'll get. Okay, so now I'm going to define what I mean exactly by short cycle. So bear with me, this name is slightly misleading because since we are working with minus log in like the actual graph, but the weights, when I'm talking about cycles, I've just removed the minus log in the weight. So when I say short cycle, it actually means that its weight is quite large. So we define this function f for all integers, and fi is equal to 2i factorial to the power 3, and any high enough power of factorial should be good for f. But a cycle in this exchange graph is called an f violating cycle if the weight of that cycle is greater than f of the length of the cycle divided by 2. So by length, I mean the number of edges in the cycle divided by 2. And one of the main lemmas in our paper is that for any feasible set S, which is at least e to the minus 10 d log d away from the value of the optimal solution, there exists an F violating cycle in the exchange graph of S. So this also, if a cycle C is F violating, that again, like I was saying, that implies that the product of these coefficients of all the edges of this cycle is at least f of length of C by 2. And so similarly to the matroid, just the weighted matroid intersection case, where we were exchanging on the negative cycles with the minimum number of edges, here we'll exchange on F violating cycles with the minimum number of edges. So by minimum F violating cycle, I mean that it's an F violating cycle and no cycle which is like a strict subset of this cycle is F violating. Okay, so moving, and I'm going to provide some intuition for why this lemma is true.
Yeah,
And
Aditi, yes.
Yeah.
Just to be like, what do you mean no subset is a minimum? No, you mean you'll connect the edge? Like it's you're looking at a cycle as a subset of vertices rather than a subset of edges in this minimality definition.
Yes, exactly. So and the subset of
vertices.
Yeah, so vertices. So it can have like a different arrangement of edges. Like you can consider chords of the cycle, or but like just the subset of the cycle should be a strict subset of like this current cycle. Okay. That's a good point. Okay, so now given our current basis S, and assume the optimal basis is some t. So, and the weights are again defined by using this matrix A. If we write Vs is equal to Vt A transpose. So, since everything is d-dimensional here, we get determinant of Vs transpose is equal to determinant of Vt transpose times determinant of A squared, just because they're all d-dimensional, so I'm just breaking up the determinant. And now, so suppose our solution S was very suboptimal compared to this optimal solution T. So say the determinant of Vt transpose was greater than the determinant of Vs transpose times the dimension d to the sum alpha d. So here, think of alpha d as like 10, which was the value in the lemma before. So alpha is a constant. Then just from this equation here, we'll get that the absolute value of determinant of A would also be large. It would also be d to the some constant d, right? So now I'm just taking this expansion of determinant over all permutations here, right? In this matrix A. So notice that all entries in A are exactly the edge weights in this exchange graph that we have. So right now in this picture, I'm just showing all the back edges in this exchange graph. So these are all the edges which don't have any weights. And if I consider a specific permutation in this expansion of the determinant, so here, say I'm considering this permutation 1, 3, 2, 5, 4. So this corresponds to these orange edges that are forward edges in this graph. And if you see, this forms a cycle cover of this graph, right? So there is a bijection between permutations and cycle covers in this exchange graph. So basically, we can say that the absolute value of determinant of A is less than equal to the summation over all cycle covers of this exchange graph times the product of weights of cycles in that cycle cover. So basically, since there are d factorial cycle covers, one for every permutation of A, there must, and since I've assumed that a determinant of A is larger than d to the some constant times d, there just by using Markov like averages, there must be at least one large cycle cover in the exchange graph of S, and that cycle cover gives one of the cycles in that cycle cover will be an F violating cycle. So okay, so now I can finally state our algorithm. So our algorithm is just, again, initialize S with a feasible set, feasible basis. So by feasible, I mean it is in the partition matroid and its determinant is non-zero. And while there exists an F violating cycle in the exchange graph of S, select C to be the minimal F violating cycle in the exchange graph, and update S to S delta C, and then just do this step iteratively till there are no F violating cycles in this graph, and return S. Okay, so yeah, this is just an update on the blue cycle again. Okay, so now you might be wondering, like when you do this update, what do you gain from this, right? Like S delta C might even have a worse objective than the current solution S, right? So this in the next section, I'm just going to talk about a very high level of idea of why when you exchange on a minimal F violating cycle, your objective actually always increases. So, and in that context, this is like a local search algorithm where you're just greedily moving from the current solution to like a better solution and you keep on moving to a better solution till you cannot find a better solution. Okay, so right, again, we have the current basis S, and assume that you found a minimal F violating cycle C in the exchange graph of S, and let T be the updated basis, that is S delta C. So here on the left, I have this in the exchange graph. So like in this left figure, T is all these vertices UI to U1 to U5, and S is the vertices V1 to V5, and these edges are exactly the minimal F violating cycle C shown here. And so let AC be the coefficient matrix between T minus S and S minus T. So what I mean by that is that there might be some additional vertices here in S which you do not exchange, like which remain the same in this iteration, but we don't care about those vertices for now. We only care about the vertices which appear in the cycle. So this is like, I guess, a submatrix of the coefficient matrix of all these U1 to U5. So Aij here is exactly the coefficient of Vj in the linear decomposition of Ui. Okay, so it's not very hard to see that the determinant of Vt transpose is equal to the determinant of Vs transpose times determinant of this AC square, where AC again is only the submatrix of coefficients which actually get changed. So like there might be other coefficients here too, but we don't care about them right now. Okay, so now if you want to prove that you actually make some progress when you change on that cycle, we want to just prove that then the determinant of AC is large for any minimal F violating cycle, right? So yeah, this problem just then reduces to bounding this determinant of AC. And what do we know about this matrix AC? We actually know that, okay, in this picture, we actually know that this A11 edge, so, okay, actually we know that this, okay, these vortices should actually be shifted. So V2 should be V1 and V3 should be V2 dot dot dot. So these diagonals here correspond to exactly the edges which appear in the F violating cycle. So we know that the product of the diagonal entries of this matrix AC is large. It's greater than F of the length of this cycle C divided by 2, right? And I guess the other complement to the previous lemma that I said is that for any minimal F violating cycle C, the determinant of AC is actually 1 plus minus small of 1. So you can think of the small of 1 as like epsilon, just epsilon. This goes to 0 as dimension goes to infinity, times the product of all the edges that, the coefficients of all the edges that appear on this cycle. And because we know this, this product is large because this cycle was F violating, we conclude that determinant of AC is at least 1 plus minus small of 1 times F of length of C by 2, which is greater than 2 because if you remember, F is like factorial cube. So F is a very large number. F of any C is a very large number. Okay, so then to just conclude, if C is a minimal F violating cycle in the exchange graph of S, then determinant of the set that you obtain on exchanging on this cycle C is at least twice the determinant of your current solution. So determinant doubles on every update, and therefore you only need a polynomial number in D updates. So this would be a polynomial time algorithm. How much time do I have left?
About 12 minutes.
12 minutes. Oh, okay.
Yes.
Okay, so then I can give a high level idea of the proof of this lemma, the first lemma, that y is absolute value of determinant of AC proportional to just product of its diagonal entries. And for this, again, we know the product of diagonal entries is large, and what we can do is we can use the minimality of this cycle C to bound all the off-diagonal entries in terms of the diagonal entries of this matrix C. So, okay, let's consider just the upper triangular entries of this matrix AC. And because these coefficients Aij, the absolute value of Aij is exactly the weight of the edge from this vertex Ui to vertex Vj. So here I'm considering the weight of the edge of from vertex U1 to V3 in this picture. So this is like a shortcut for your cycle. So if you ignore all the other edges, then you can compare this like path that you get from U1 to V3 using this black shortcut versus the path the cycle actually takes using which is it goes from U1 to V2 to U2 to V3, right? So if you compare these two paths, we'd get that the absolute value of any Aij is bounded by the absolute value of the products of sorry, this should be ATT. ATT, where T goes from I to J. So basically, what I'm saying is that the absolute value of this black edge is bounded by the weights of these two orange edges times this function of the f that we define. So here it's to be concrete, it's fk minus j plus I divided by fk. And similarly, I'm going to do a very analogous thing to bound the absolute values of lower triangular entries in this matrix AC. So every lower triangular entry corresponds to like this back edge in the exchange graph. So here I'm actually showing back edge from U4 to V2. And this corresponds to the entry A4, comma 2. But now you can see that this back edge actually forms a smaller cycle with the edges in your cycle C, right? But we know that because C is the minimal F violating cycle, this cycle cannot be an F violating cycle. So this again gives a bound on the value of this black edge in terms of all the orange edges in this cycle. So finally, putting these two complementary things together and doing some linear transformations, we get that the absolute value of determinant of AC is equal to the weight of the cycle C, so which is exactly the product of all the coefficients on the edges of C times determinant of this matrix here. So let me parse this matrix for you. So all the diagonal entries of this matrix are exactly 1, and all the off-diagonal matrix of these off-diagonal entries of this matrix have their absolute value bounded by the functions of f that I've written on their corresponding squares. So what this means is that, like, if we take the first lower triangular off diagonal, then absolute value of every entry on this off diagonal is at most f1. And similarly, if you take the first upper triangular off diagonal, then the absolute value of every entry on this diagonal is at most fk minus 1 by fk. Also, sorry, I should have mentioned this earlier. K is the number of edges in C divided by 2. So like in this cycle with 5 vertices, K was 5. Okay, so now this matrix looks almost like a toplets matrix, but except like all the entries in the upper triangular have this fk in the denominator, so we can't use any of the nice theory there. But nevertheless, if we play around with the entries of this matrix, we can see that all the permutation, like all the permutations of this matrix, except this like diagonal permutations, they are very small in magnitude compared to 1. And after some careful counting using dearrangement polynomials, we can actually prove that the sum of all the non-identity permutations is also very small compared to 1. So what this means is that when you write the determinant of this colorful matrix in as like an expansion over the permutations, only this orange permutation, so the identity permutation, dominates the determinant. All the other terms are negligible. So what this means in essence is that the determinant of AC is actually the weight of the cycle C times 1 plus minus small of 1, and again think of small of 1 as going to as a very, very small number. And so this would always be greater than 2 no matter the value of k. And so that means that the change in determinant is always greater than 2, which is what we needed in the lemma to ensure that we are making progress in every iteration. So this concludes the technical. This concludes my talk. So in conclusion, I talked about the determinant maximization problem and how it can be used to model a wide variety of optimization problems. And I showed one of the past combinatorial methods for approximating this problem with provable approximation guarantees. And just to emphasize again, this the algorithm that I talked about improved the best known approximation factor when rank is less than d, from e to the d squared to d to the d. And in an ongoing work, we also proved that these techniques can be extended to the case when rank of the matroid is greater than d. And we actually combine some previous work in this area about sparsity of convex program with these combinatorial techniques to give this approximation. When rank is greater than d, we give a d to the d approximation. And some related open problems is, so there is still a big gap in the lower bound and like this approximation bound. So the lower bound is only some constant to the d, while right now we can only approximate it to d to the d for general matroids. Another interesting open directions is there is a bunch of related problems in design, in optimal design theory, where you consider different spectral objectives. So here we consider determinant, but one can also pose a question of finding minimum of the trace of inverse of this sum of VI transpose, or finding the maximum of the minimum eigenvalue, or minimizing the maximum eigenvalue. And the last problem is especially interesting because under partition constraint, the lambda max objective is closely related to the Cadison-Singer problem. So you can reduce the, in this paper of MSS in 2014, they showed that you can reduce the Cadison-Singer problem to finding, to minimizing lambda max under partition constraints. And again, like, I guess the overarching message I want to of this talk is combining algebraic and combinatorial techniques is a very powerful tool, and I think combining these techniques can also give very interesting results for other problems too. And so this concludes my talk, and thank you for your attention.
Any questions for the speaker?
Hey, Aditi, quick question. So, like partition matroid does satisfy sort of other stronger properties, like it's strongly like base ordering and so on. So, what that means is that in the exchange graph you have more structure, so to speak. So you can find, for example, a matching such that if you swap any subset of the matching, the independence is maintained. So you can do a lot, like not just maybe cycles, but you have stronger sort of exchange properties or swap properties that in particular for the partition matrix. So has this been exploited or?
So for this algorithm, no, we did not exploit any properties of the partition matroid because I guess the main thing in the cycle that we wanted was like the minimality and being F violating, because those are the properties that we know would imply like an increase in determinant, which is quite independent of like being a partition matroid. But this property of like exchanging on the shortest cycle
Right.
with minimum number of edges in any weights, this is true for like any matroid. If you exchange on such a cycle, you'd always be in you always go to a basis of that matroid.
Got it. Okay, thanks.
Yeah.
Any other questions? So what does this constraint look like? The C power D lower bound?
I am not very sure, but I think it's one point something. I think.
So how do you show the hardness here?
The hardness is from I think a reduction from label covering. It's in the paper by D. Suma et al. Which also gives like a related approximation algorithm.
Okay, thanks. So if there are no other questions, let me thank the speaker for the talk. And maybe Ramesh, you can stop recording.